This video will describe the classic voltage divider and the meaning of the term voltage drop. At the end will be a short lab which will confirm the theory. This is a very simple circuit consisting of a single 6k resistor, a resistor decade box, 2 voltmeters and an ammeter. But first we'll go through the theory. Okay, all we want to know in this arrangement of a battery connected to 2 resistors is the proportion of the 12 joules of energy per coulomb from the battery that is burnt up by R1 and the amount burnt up by R2. I say burnt as that is pretty much the way most of the battery's energy gets used in electrical circuits. The energy from the battery gets directly converted into heat energy by both the resistors. So in the sharing of this energy usage, it's only the proportions that matter. So the 6 and 18 could just as well be 600 and 1800 or 6000 and 18,000. Using the bigger resistance values though is wiser here, as it means it will take a lot longer for a coulomb to flow through, i.e. a much lower current. The energy is then released over a longer time interval, i.e. lower power. So there is far less chance things will catch fire than using say 6 and 18 ohms resistors, for example, on a 12 volt battery. So the total obstruction going with the 6 and 18 is 6 plus 18 equals 24 say units of obstruction, if you like. It's clear that 18/24 of the 12 joules per coulomb are used up by R2 and 6/24 of it are used up by R1. Now it's very convenient to use a formula for this which will help us remember the above. This is called the voltage divider formula. It simply shows us the proportion of energy per coulomb burnt by each resistor of these 2 resistors connected in series with the battery of source voltage Vs, with VR being the amount of energy released per coulomb of charge that flows through the specified resistor. So if we're looking at R1, then we're saying VR1 equals R1 over R2 at R1 times Vs. If we're looking at R2, then we use this one. VR2 equals R2 over R1 and R2 times Vs, the voltage source. This is all that most textbooks or educational institutions will cover on how voltage dividers work, because they will make the reasonable assumption that by this time you will know at a deep level what voltage is and how energy in circuits behave. But if the concepts of energy and voltage are not understood to this point, then the fact that the voltage at V0 is equal to 9 volts here, so I've calculated it, that won't mean much. That won't mean very much if you don't understand the concepts of voltage and energy too well. Even though you could still use the above formula and analyse circuits and even get the correct answer, 9 volts, no problem. So what I'm going to do is to assume to this point you're not 100% okay with voltage and energy in circuits. So I'll describe what is happening in this circuit in very close detail, and after that is over you will know how electrons flow in this circuit, and you should then also get the concept of a voltage drop. So before we talk through this voltage divider in a lot more detail, let's first look at a much simpler circuit to get us started. Now here, for every coulomb of charge that cycles around this very simple circuit, 12 joules will be used up by the resistor. Does not matter what size the resistor is, 12 joules will always be burnt up per coulomb that flows through it, all the while the battery is connected. Now, if the resistor is very small, then charges will flow faster through the whole circuit, so the 12 joules will then get used up much faster. But if the resistor is very large, then it will take much longer for a coulomb of charge to flow through, so the 12 joules will take much longer to get used up. So that's the basic point here of what voltage is. Now, let's have a look at a very simple circuit. So this is just a wire connected to a battery. Now we've got a 12 volt battery will always provide 12 joules of energy to any circuit we attach to it for every coulomb that passes through, no matter how simple or complex the circuit happens to be. So this could be really complex. Doesn't matter. Could be simple. It's always going to release 12 joules of energy once a coulomb goes through it. Now, why will it always release it? Well, it's because if we're looking at this now for charging, it's because 12 joules of external energy from a power supply, say, was used up for every coulomb that was originally separated out. So this charger here is separating out the charges into plus and minus charges onto the plates of the battery. We call that the charging phase. So that when we allow the charges in a circuit to come back together, so when we're looking back at here, so when we allow these charges to come back together again by connecting the two sides with an external wire, that same 12 joules per each coulomb will then be released. So the 12 joules we put in through the supply will then be released per coulomb. Makes sense? And that will continue until the battery's chemicals are exhausted. So this is what voltage means. All the while a battery is not connected, we can say it has a potential energy of 12 joules per coulomb. When we connect a 12-volt battery to any circuit, those 12 joules of energy will always be released for every coulomb of charge that flows between its terminals. So I sort of laboured the point there, but I think I hope that makes sense. So what about how fast a coulomb actually flows through a resistor? Well, if we use a really small resistor, the separated charges in the battery will see a smaller obstruction to their desire to get back together, and so they will all move at a higher current through the wire. So then a coulomb now flows through much quicker, which means that the 12 joules will also get used up quicker by the resistor. The number of joules released each second by the resistor we describe as how much power the resistor uses, since power is joules per second. Now, if the resistor is really small, then the energy will be released extremely quickly. Say the resistor is at 1 ohm, that energy will be released really fast. So then we have a lot of high power across the resistor. If power is very high, the resistor could even explode. So at 1 ohm, it almost certainly will explode. We want to avoid resistors getting fried, so a larger value of resistance will let the 12 joules of energy get released much more slowly, as the number of coulombs passing through per second would then be reduced. So with less power, we reduce the risk of destroying the resistor. So to summarise, the amount of coulombs that flow through a circuit each second we call the current, which is coulombs per second. The energy that a battery will lose per each coulomb that flows through the circuit is the voltage, which is joules per coulomb. So if we multiply the number of coulombs that are flowing through a circuit each second by the amount of energy the battery burns up across the circuit per coulomb, we get the power that is being produced by the circuit, which is P equals I times V, joules per second. Now, just make sure everything I've said so far makes sense, and now we're going to return to the divider circuit, the voltage divider circuit. Now let's look at this divider circuit again, but this time from the charges point of view. Here it is redrawn with the circles represent large globules of charge. So each of these little circles represent a large amount of charge. The volt, and everything's all packed in here. The voltmeters have very high resistance, so these have got very, very high resistance in the mega ohm range and require very high voltage to move their needles to full scale. The meter B as we calculated before, the meter B will be showing 9 volts and this meter A will be showing 3 volts. Now, to get a feel for this, we have to realise that all the wires shown are packed with charges before we even connect up a battery. When we connect up a 12-volt battery, then all of those charges will all move everywhere in the circuit at almost the instant the battery's last terminal is connected. They all start moving, all nudging each other. All the charges are then under tension, caused by the electric field forces between the plus and minus terminals of the battery. From this, they all move along, positive charges moving from plus side to the minus side, at a fixed constant rate of charge flow, the size of which is dependent only on the total amount of obstruction the circuit has in it. More obstruction is more resistance to charges flowing. Less obstruction, less resistance. So all charges will move along quicker if there's less obstruction. For each coulomb of charge that moves through the circuit, 12 joules will always be used up by the two resistors. Now from the battery plus to the top of the A voltmeter here, the charges are seeing a much smaller obstruction through here R1 than through R2. So that means we have less charges flowing through the A voltmeter. So A will show a lower joules per coulomb reading of 3 volts. We say R1 is showing a voltage drop of 3 volts across it. Now looking at the connecting wire from the bottom of A here and the connecting wire from the top of B, so look in here, the charges in this section of the circuit are seeing a much greater obstruction through R2. So that means many more charges at this location will flow through B, the voltmeter B, then flow through the voltmeter A. And so the voltmeter B needle will show a higher deflection of 9 volts. We say R2, we say this resistor here is dropping 9 volts and has a higher voltage drop than R1. So now I hope you can see not only what is happening inside a voltage divider circuit, but also what is meant by a voltage drop. So just to repeat this again, a voltage drop is how much energy is consumed by a component per coulomb that flows through it. If the coulomb flow rate is high, then the energy will be dropped faster across it, high power, joules per second. If the coulomb flow rate, i.e. current, is low, then the energy will be dropped more slowly across it, low power, joules per second. Now look at the top of the connecting wire that goes into B. So if we look here and imagine that R2 is an infinite resistor, where then will all the charges go? So this is an infinite resistor, so it's, you can think of it almost as an open circuit. Where will the charges go? They can only go through B, the voltmeter B. So the B needle will show 12 volt as all the energy per coulomb is then used up across the voltmeter. We say that all 12 volts is dropped across the voltmeter. In other words, all the battery's energy per coulomb is burnt within the voltmeter. But remember, the resistance of voltmeters is in the mega ohm range, so although we drop all the 12 volts across it, it will take years for 1 coulomb and hence 12 joules to get used up by it. Very tiny current. So what we're saying here is this voltmeter has a massive resistance, yeah? So although R1 has a resistance, it's so insignificant compared to the massive resistance that the voltmeter shows to the circuit, then all the energy, nothing in comparison, proportion, all the energy is dropped across the voltmeter. So the voltage is all dropped across the voltmeter, and this is insignificant compared to the amount of the proportion that's dropped across here. So in effect we say that the whole 12 volts is dropped across the voltmeter. Right, so that's kind of really explains the voltage divider in excruciating detail. So just to finish this off, we're going to do a quick lab. What we're going to do is first, by using the two resistors, a 6 kilo ohm and an 18 kilo ohm, confirm the 9 volt and the 3 volt drops by using 2 voltmeters. Then I'm going to replace the 6 kilo ohm with a decade box in the circuit. We will insert a current meter as well. Then we'll run through a number of resistor values here and tabulate this table. What we want to confirm is that the larger values we use of resistance will cause both voltmeters to show different proportions of the battery's supply of joules per coulomb, the voltage, basically to confirm what we've just discussed here. So when we fill this in the lab, we'll discuss it as we go along, and you'll be able to see the actual numbers that are produced to back up everything we've just discussed.